Hello, everyone. Welcome to Rational Science from Frankfurt, Germany, live. Today we're going to talk about, well, we're going to not talk about, we're going to have a tour. We're going to have a tour through the particle zoo of quantum mechanics. Now, how's that for a subject? Okay. We're going to do a little revision of what these people have found over at least specifically over the last 100 years. Okay. Okay, so where do we start? Well, we have to start in the 19th century to get our bearings. 19th century was a century of waves. Everybody believed in waves. Early on in the century, you had people who started contradicting Newton. He was the Einstein of those days. And so they challenged him. They said, look, we can't explain what we see in the lab with particles. Newton was a particle guy, right? And so you had all these other folks, especially the French, and they started saying, it looks like you're confused, Newton. Looks like light is really mediated by waves of some kind. It's got this wavy, vibrating, oscillating motion in there. And so they believed in waves. And you have people like Thomas Young, who in England proposed the slit experiment. He tried to explain that with waves. And then you had Augustin Fresnel in France. He was able to explain not only the slit experiment, but later on polarization with waves. And so the wave was, introduced and grounded in the minds of the mathematicians. The question that came up in their minds, which probably also happened in the 18th century, before that, was what was it that was waving? And of course, everybody said, well, it's the ether. And the ether was a notion that came from the days of the Greeks. That was this bunch of particles that filled the vacuum, or that was the vacuum, either filled or was the vacuum. Some people equate it with a vacuum. Some people say, no, it just fills the vacuum, like the vacuum's something else, okay? And that's the big problem. People have never been able to define what space is. They don't understand what space is. We cannot relate to what space is because space is nothing, and we're not used to nothing. We're always used to, we deal every day with somethings, not with nothings. And so when people say, look, space is nothing, well, what do you mean by that? Or what does that mean? And so, yeah, they turned space into something. The Greeks did, and everybody to this day thinks that space is something. Quantum mechanics, mathematical physics, completely, general relativity, string theory, they all treat space as something. What was that something in the 19th century? That something was the ether, okay? And really nothing's changed. Today we gave different names to the ether, but the ether is still there. The ether is this body of particles. That's what it is. That's what the ether has always meant. People who are outside of that don't understand what the ether is. They've got tiny brains because they cannot relate to what ether is. Ether, bunch of particles. Okay? So that's what happened in the 19th century. What was waving was the ether. Well, towards the end of the century, a couple experiments indicated to the mathematical community that there was no ether. Okay? Whether that was true or not, irrelevant. The point is that people believed it. People stopped believing in the ether as a medium, or they started suspecting, questioning. And what came immediately after that was quantum, exactly at the turn of the century. We have Mr. Planck. He says, light comes in discrete packets. And in Einstein, 1905, he came up and he used that. He quantified that to explain the photoelectric effect. And from then on, we had the particle again. So the turn of the 20th century, from the 19th to the 20th century, was a major revolution because they went back to Newton. They said it's particles. Except for one little teeny weeny detail, and that's that the particle was not a particle. The particle was a number, was a value, was an amount, was a quantity. It was no longer a little ball. It was not a corpuscle. It wasn't a speck of dust, a ball. And that's what we have today. We don't have balls. To this day, no balls, okay? It's all numbers. These are mathematicians talking, not physicists, okay? So when you listen to a mathematical physicist, especially a quantum mathematician, quantum physics, or string theory, when they talk about particle, when they use the word particle, they don't mean particle. That's just misleading. That's a euphemism to mislead you, to make you think that we're talking about a little ball, which is what they're going to use to illustrate their physical interpretation. but it bears no relation to what they do in their offices. In their office, they talk about one thing and one thing only, and that's numbers, quantities, values. Okay, so when they accelerate or smash, they're not accelerating or smashing balls. What they're doing, what they're doing is they're accelerating and smashing number 5s and number 10s. They're smashing a 9 against an 8. Okay, you got to keep that in mind, because that's the problem. The problem is these people are using abstractions, and that's what they say is happening physically in the lab, in the accelerator, at the LHC and so on, SLAC, Fermi Lab, Brookhaven. Okay, so early on, the first 20 years, they tried to figure out, what that invisible world was that they had out there. What was this world of atoms? Okay, because they had already come up to speed on the idea that, that there were atoms out there, that there were particles. That's the way they saw it, flying around. They said, well, air is made out of particles, water is made out of particles, iron is made out of particles, everything is made out of particles, atoms. And they were trying to dig deeper into the atom to find out what the atom looked like, okay? Partly because they wanted to develop technology, okay? That was part of the issue. There was this invisible world. They were trying to pry it open, to peer inside there, okay? And so first we have these two gentlemen, one in 1913, make them a little bigger. Here we go. 1913, Niels Bohr, he came up with this planetary idea, planetary model of the atom, and that was more or less confirmed in the minds of the mathematicians when in 1919 Rutherford does his gold foil experiment and realizes or proposes that the atom is mostly empty space, and it's got some what he called positive charge in the center. The positive and negative labels were given by Ben Franklin 100 years earlier. So he comes up with this, and he says, okay, we have a proton in the center, that's the positive charge, and we have the electron on the outside. This was the model. And with this model, they lasted for the last 100 years, essentially. This is the model that we have today. This is you might say, well, this is not really the model of quantum mechanics. Well, I don't care what the model of quantum mechanics is, because this is the model they use for everything, to explain everything. That's where the problem is. So if quantum mechanics has a different model, the cloud model, the whatever model out there, the layered model or the orbital model, we don't care, because it has no bearing on what people are taught and on what and how they explain things. When you explain quantum jumping, when you explain electricity, and when you explain ionization, that's the model they use, and that's the only model they can use. So this is the model. Sorry. If you got a different model, draw it. After all, they claim that they've seen these, that they've photographed them, and that they whatever, that they shook hands and interviewed them. Fine. Draw it. I need to see your atom, if it's not this one. Otherwise, this is it. Okay? And so this is the model they used. And, of course, they realized there were problems with this model. One of the big ones was that if the electron was just circling around, why didn't it fall towards the nucleus? Good question. First of all, what keeps the electron from flying away? Second, what keeps it from falling in? I mean, is it running on a track? Is it on a roulette kind of track? Why doesn't it fall in or leave spontaneously? And that was the problem with that model. They realized that it was a mathematical model only. They could explain it mathematically. They say, okay, this guy goes around, and this more or less mimics what we saw in the lab. Okay, solid proton, positive proton center with the electron flying around somewhere. Okay, fine. So this was the notion they had, but they have no way to make sense of it. Okay, and to this day they can't make sense of it. Okay, what happened was that there was a phenomenon going on, and that was beta decay. They were aware of beta decay, that an element could transmute into another simply by having what eventually became, because at the time they had no idea why that happened. Okay, so they were trying to figure out, they were trying to propose theories of what was going inside the atom that would explain this beta decay, this transmutation. Okay, and so Pauli, Wolfgang Pauli comes up, and he comes up with this model. He says, there's another particle in there somewhere. Okay, and this is these are his own words here on the right. I have hit upon a desperate remedy to save the exchange theorem of statistics and the law of conservation of energy. What happened was that he had a little debate with Niels Bohr. And Niels Bohr said, this is a statistical fluke, a statistical issue. And that would have given jobs to a lot of statisticians and kept the so-called mathematical physicists out of it. And so Pauli said, no, 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 no. I can give you a better idea. I'm going to create a new particle. And that's going to set the equation right. Okay. So he said, namely the possibility that there could exist in the nuclei electrically neutral particles that I wish to call neutrons, which have spin half and obey the exclusion principle, which is what he had developed in 1925. By the way, you know, by 1927, they had all these principles that formed the foundations of quantum mechanics. One was the exclusion principle, for which Pauli gets the Nobel Prize eventually. And then there were two other principles, one by Bohr, the complementarity, and the other one by Heisenberg, which was the uncertainty principle, for which he won also the Nobel Prize. Okay, so these foundations were established before any of the particles that we're going to talk about today ever came into existence, before they ever ran any experiments. So they already set the foundations of quantum mechanics, and generation after generation has simply memorized these foundations, these cornerstones, right? Okay, anyways, he said that I wish to call neutrons. Okay, so he's the guy who invented this word neutron, and we'll see what happens with that word, which have spin half and obey the exclusion principle, and which further differ from light quanta in that they do not travel with the velocity of light. Okay? The mass of the neutrons should be of the same order of magnitude as the electron mass, and in any event no larger than 0.01 proton masses. In other words, it was very low mass, the particle he was suggesting, traveled almost at the speed of light. Okay? And the word neutron meant that it had no charge. That was important also. It had to have no charge because it would have upset the balance between electrons and protons. The continuous beta spectrum would then become understandable by the assumption that in beta decay, a neutron is emitted in addition to the electron, such that the sum of the energies of the neutron and the electron is constant. Okay, so this was an accounting procedure that Pauli suggested or invented, right? He had to win that debate with Bohr. That was essentially what it was about. Okay? One guy said, look, it's just an accounting procedure. We've got a little, fluke in the statistics. It was a statistical fluke. Bohr said that, and then Pauli, on the other hand, she said, no, 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 there's a particle in there. And so they invented the particle to make the equation come out right. Okay, keep that in mind. Okay, that's how it works here. Okay, you first do the equation, you see something's missing in here. Okay, put a particle in there. That's how it works. And then they tell the particle accelerator people, the particle mathematicians, the guy who work at the lab, say, go find it. You're looking for a particle that has no charge, that has so much mass, travels at the speed of light, has so much spin, etc., etc., etc. And so that's what they look for at the lab. They go to the lab and they say, okay, we're looking for this monster. It has all these properties. That's what the guys, the theoreticians upstairs, that's what they want us to look for. And that's what they look for. And then when they find it, the theoretician and the experimentalists, they both get a Nobel. That's how it works. Who gives them the Nobel? Their buddies. Because they were able to convince them. That's how it works. That's the system. Okay. Okay, so here we have Mr. Chadwick. He comes around the same time. He published his paper in 1932, but he was already working on it, for the last couple of years. Okay, and so Chadwick says, look, I found out something very strange here. It turns out that helium is element number 2. And so if hydrogen is element number 1 and helium is element number 2 and has 2 charges compared to 1 charge for the hydrogen atom, well, how do you explain that? Well, you just have 2 protons in there and 2 electrons. We're done. But that wasn't the case. When he ran his experiment, he realized that helium weighed a little more than just 2 hydrogen atoms. In fact, it weighed almost like 4 hydrogen atoms. And so he said, well, how do we explain this? And that's how the neutron came to be. The neutron had to have no charge, again, because it would upset the balance between electrons and protons on the one hand, but on the other hand, it had to have mass. In fact, the mass approximately of the proton, in fact, a little more than the proton. And that's the guy that Chadwick discovered or invented. That's what he proposed, and he was given a Nobel for that. And so if that was the neutron, because that was inside the atom, then what was this little particle that Pauli was talking about? Did that exist? How can we make sense of that? And that's when Fermi, Enrico Fermi, an Italian guy who eventually worked on the bomb in the United States, he talked to Pauli, and they had a chat. He liked the idea that Pauli proposed, and he went out there and did all the math for it. He tried to figure out if that particle could exist. Was it even in the works? Was it a possibility? Okay. And so Fermi comes around 1934. He publishes his paper. Okay. And he says, this is what happens. What happens is we're going to name it a neutrino. Okay. So they gave it a new name instead of the neutron. Chadwick had stolen that one. Okay. So they said, okay, the neutrino comes out together with the electron. And that's where the transmutation occurs. A proton is, because you have, for example, this is just an example. Carbon-14 turns into nitrogen-14. And so the issue is you go from 6 protons and 8 neutrons, and you go to 7 protons, 7 neutrons. And so a proton changed into a neutron. And then you have also in other cases where neutrons turn into protons. Okay, so that's the exchange that you had to explain that transmutation. How does a proton gain or lose charge and become a neutron? How does a neutron, gain charge and become a proton? That was the issue. And the weights, the masses had to remain the same. And then eventually also we had this issue of spin, which is going to come some years later. Okay, so he gives an explanation. Actually, this is a theory. This is an explanation of what's happening in there based on particles. If particles exist, yeah, this is what they're talking about. But the issue here is that, again, these are not particles. Because when a mathematician talks, a quantum mathematician talks, he doesn't talk about particle, he talks about mass. And he talks about charge. That's what he talks about. And so when you say, well, particle, are you talking about a speck of dust, a little ball? No, it's we're talking about mass. But I thought physical objects were the ones who had mass. Okay, so this is where the problem is. These people are talking about mass and charge. They're talking about their equations, their numbers, their calculations, their, what they do in the office. And you want to know about physics. You want to know what's physically going on in there. So they illustrate it like this, but that's not what they really mean. They're in a different world altogether. They're just talking about numbers and quantities. Okay, so it's important to keep that in mind. Otherwise, you lose track of what quantum really is about. Quantum is not a particle theory. Quantum is a mathematical description only. Okay, they just try to describe what's happening in the invisible world out there with equations and by creating all these masses and charges and spins. They put them into what they call a particle, which is not a particle, but they have to illustrate something for you to understand them, so they put a ball. And they say, yeah, that little ball, that's the electron ball. And it's got so much charge, so much mass, so much spin. That's how they do it. But when you say, well, what is the electron? Can you draw it for me? Well, we don't know what the electron is, and that's not important for us. For our world, the world of math, quantum math, we're just concerned about these quantities because that's what we can put in an equation. We can't put the word ball in an equation. We can't say, well, ball plus ball equals what? Square or a cube? They can't do that. They can't put an elephant and, I don't know, a rhinoceros in an equation. They have to put the masses and how they're spinning and if they have charge or neutral, that sort of thing. That's what they deal with. So until you get a handle on that, you really have not grasped what quantum mechanics is about. Okay, you have to understand the world of mathematicians. Okay, a year later, after Fermi came up with his idea, Yukawa proposes something else. He's a Japanese fellow. I talked about him the other day. And he says the interaction energy calculated on such assumption is much too small to account for the binding energies of neutrons and protons in the nucleus. He was trying to solve the issue of what's happening inside the nucleus. Why doesn't the proton expel another proton? That was the issue that was in their hands, that they were trying to solve. And so he invents a new particle, the meson. Okay, meson. The transition of a heavy particle from neutron state to proton state is not always accompanied by the emission of light. Okay. Light particles, neutrino and an electron, but energy liberated by the transition is taken up sometimes by another heavy particle, which in turn will be transformed from proton state into neutron state. And that's when he proposed the meson. Okay, I like to call them mesons. Used to live in Mesa, Arizona, so I call them mesons. Okay. They were again trying to find all these particles that were part of the nucleus. They were going deeper than what Rutherford had gone in 1919. He just did a gold foil, relatively simple crude experiment compared to what came later. What came later, they started smashing particles, breaking them apart, and say, what kind of debris do we get out of all this? Okay, and so one of the guys that did that, who ran these, was Carl Anderson, and he came up with what I call the suppositron. He called it the positron. I call it suppositron because he supposed that he was dealing with particles. And essentially, he saw a mark on a plate, lead plate, and so he says, that was made by the positron. And he said, well, how do you know that? Well, see, they had these magnets on the sides, and if the particle went right, which is what it was supposed to, in the direction in which it was supposed to go, because you had the magnets put in that direction, then it was an electron. They said, well, this would have been an electron. It turns out that the particle went in the other direction against the magnets, and they say, oh no, this is a positive particle. And because of the mass and the speed and all of these other issues that they looked at, they said, oh, this is not a proton, this is not a neutron, this is a positive electron, a positron. Okay, so he got a Nobel for that. Okay? Nobel smiled at him. Okay, so same year he also discovers the muon. Okay, and with the mu meson that they thought was what Yukawa was searching for. Okay, which the particle that Yukawa had identified, and it turns out that this was too heavy to be the particle that Yukawa was thinking of. So they said, no, this is a different particle, and so this was a mu meson, and they call it the muon. Okay, and from that point on, they said, okay, where did this guy come from? And that one also came from the sky. One of those particles, cosmic particles, okay? Okay, so they were starting to discover all these particles, and just when they were almost there, World War II breaks out, okay? So once World War II breaks out, all that effort in civilian physics was diverted towards military purposes. And especially, the development of the bomb. Some of these physicists were put into rocketry, and so on, and developing better airplanes and so on. And others were put into the nuclear program, secret in different countries. The British did it, the Germans did it, the Americans did it. And so they went out there and they tried to figure out, if they could, because they had proposed that you could produce a big bang from atoms, especially from uranium. And when the politicians caught a whiff of that, especially the military, they said, oh, hold it, let's see, maybe it's worth investigating. A lot of them were skeptic. They said, well, it's not going to happen. So they took all these physicists, so-called physicists, and they put them into work, as theoreticians. For example, the Manhattan Project that developed the bomb in the United States. There was another one in Britain, and Germans were working on that. So they were all working in secret on these projects, and for that they needed all these mathematical physicists who were working on the atom. Okay, so there was this interregnum, this period in which no more particles essentially were discovered. In fact, for 3 years, I think the Nobels were not given out, were not handed out during the war. And after the war, well, everybody more or less went to normal, and they went looking for particles. Okay, and in 1952, they developed the bubble chamber. They had until then they were using a cloud chamber, and I'll go over that in another day. And now they invented the hydrogen bubble chamber, and what that allowed them to do was to look for traces of particles in a little more detail. Okay, and yeah, suddenly you entered this particle zoo. They discovered particles everywhere during that decade, the 50s. Everybody was discovering particles. They said, oh, I found a new particle. Give me my Nobel. Everybody was shouting for their Nobels. Give me my Nobel. I found a particle. And, I forgot this all. And this Chadwick. Okay, just showed him a minute ago. These two fellas, they made a comment that puts it in the proper light. Oppenheimer said, the Nobel Prize should go to the physicist who has not discovered a new particle this year. And Fermi, he said, if I could remember the names of all these particles, I would have been a botanist. Yeah, I mean, they were discovering particles left and right. And so this created somewhat of a quandary, because people were wondering, do these particles really exist? Does the atom contain all these particles? Where are they coming from? And they had in the back of their minds what Dirac had said in the 30s also. Paul Dirac, he came up with this sea of virtual particles, negative and positive particles that form space. Again, the ether. particles forming space, the background particles, you know. And so a lot of people were starting to come up with this idea that some of these particles were coming in from the void, from this unseen space. They had to borrow it from somewhere for the equation, not because the particle was there out, you know, in real life, that it existed out there, but they had to say, well, how do we get this equation right? Well, put this particle. Okay, so they put the particle with all these parameters. And you say, okay, I got the particle. Now the equation checks out, but where did this particle come from? And so they had to make, you know, that reinforced in them that the vacuum was made of particles, because they had no other place from which to draw these particles. The atom was complete pretty much in many ways, right? And so they said, where are these particles coming from? And especially when they saw these cosmic particles like muons and pions, they said, you know, all this stuff is in the vacuum. Vacuum is made of these particles, or these particles fill the vacuum. They had to figure out, you know, a way of explaining that. And what they said, well, you got a positive particle and negative particle. They come together and they form a no particle. And that's essentially what Dirac had said. He had the particle and antiparticles. And so they combine to form nothing. Or like I like to say, a black ball with a white ball forms a no ball. And then they separate, the no balls separate into black and white balls. That's their world. Because they have no other way of explaining this in terms that you would understand. Okay? So when they do their calculations, they're safe. They're in their world. Nobody touches them. But when they have to go out there and explain to the layman, you know, what are we paying you all these tax dollars for, maintaining your projects? Well, let me show you. This is a white ball. This is a black ball. When they come together, they form no ball. And people look at that and say, are you kidding me? They say, hey, we're the mathematicians. Do you know more than we do? And that's what it's all about. It's all about these people just telling the crowd, hey, we know, we got the PhDs, we've done the experiments in the lab, we have the equations. You know, they could have told them anything. They could have said it's angels or spirits. It would have been no different. In fact, it is no different. There's a small difference. Angels you can imagine. Spirits you can imagine. You know, Casper the Friendly Ghost, you can imagine that. These guys are talking about quantities that are flying around. That you cannot imagine. So, yeah, it is unimaginable, meaning it's irrational. That's what quantum is. Okay, so what happened after that, we have this, just the particles galore. Okay, now we get into the particle zoo. So get ready for the tour now, okay? We start the tour. Here it is, okay? These are the milestones that we had in the last 75 years since World War II. First, they detected the mu meson, okay? The muon. In fact, it had already been detected earlier, you know, by Carl Anderson. The cosmic ones. This one was from inside the atom. In 1949, they predicted the repulsive forces between two nucleons become attractive in the nucleon anti-nucleon system, forming the pi mesons. Okay. Well, what it is that, you know, you gotta figure out how attractive, how to produce attraction in quantum mechanics, and they never figured that out. They were never able to figure out how to produce attraction. And so the way they do it is they do it in strange ways. They simply change the charge. For example, here's an example, okay? If I can find it. Here it is. Here's an example, okay? What you see is two up quarks and down quarks at the top. And what we're going to do is we're going to change these down and up quarks to the other, okay? And essentially what they're saying is this is how a proton turns into a neutron into a proton. In other words, how it gains charge, how it loses charge. Well, great. Just tell me how atom 1 attracts atom 2. That's what I need to know. I need to understand attraction. I need to understand pull. The only force that quantum mechanics will never be able to answer. They can answer push, particle against particle, but you cannot answer pull, attraction. Okay, action at a distance, attraction. How do you pull something from a distance if you're going to mediate it with particles? So what they do is they say, well, very simple. See, you have these gluons, the little two balls that are flying around, those pairs of balls. What they do is they change an up quark into a down quark or vice versa. Okay, so by doing so, you change the charge. And as we all know, positive attracts negative and negative attracts positive. And positive rejects positive and negative rejects negative. Yeah, but you haven't explained the mechanism. All you're giving me are descriptions. All you're telling me is a positive turns into a negative. What does that mean? What does that mean in physical terms? Okay, so this is the underlying problem, okay? That these folks are simply telling you that positive turns into negative, and that's how they produce attraction. because we know that the positive side of a magnet attracts the negative side of a magnet. That's all they can say. Okay, so it's not a mechanism. They haven't explained the mechanism. Anyways, 1952 they invent the hydrogen bubble chamber. 55 they discovered the anti-proton. See, now we have these antiparticles that they had to discover. Okay, and just a short time later, a few months later, they detected the anti-neutron. So now we have these antiparticles. So how does an antiparticle differ from a particle? I mean, what's different about them? The structure? I mean, structurally, what's different? And all they can tell you is that one has that when one combines with the other, they annihilate. What? Virtual particles. Where do they go? They go to form the vacuum. What is the vacuum? Made of particles, which are annihilated. So they have these dualities where you don't know if the vacuum is made of particles or made of nothing. Because if they annihilate, what did they annihilate into? Well, they annihilated into nothing, and nothing is made of two particles, or one particle, or whatever. You know, I mean, it's made of particles. So we don't know what annihilation means, because if two particles, an antiparticle and a particle come together, they annihilate, but what does that mean? What do they turn into? They turn into a particle, into nothing. If they turn into nothing, what is nothing? Okay? So again, they use this, and they leave it open-ended so that nobody asks these questions. Okay? Okay, then they also detected the neutrinos in 1956, okay, for the first time. And I discussed that the other day, Cowan-Rhine's experiment. They received, well, one of them receives the prize 40 years later. The other one died, so he didn't receive the prize. In 1960s, they were also trying to unify the electromagnetic forces with the weak forces, okay, the photon with the W's and Z's. They were working on that problem, okay, and I showed that the other day. They detected cosmic neutrinos. Okay, these again flying from stars, and they say that these neutrinos were actually created immediately after the Big Bang. There's gazillions of them just flying around, and so part of that cosmic background radiation includes neutrinos. What happened also in the 60s? Mathematical formulation of spontaneous broken symmetry in quarks. 62 discovery of the muon neutrino. They proved that there were at least two neutrinos, so now there was a search for these extra neutrinos, especially the search for naming them. Strangeness and quarks were invented in 64. Also in that year, discovery that matter and antimatter symmetry is violated when the neutral K mesons decays. Great. Okay, fine. So you can see what these people are doing, what their research is into. They're just looking at all these mesons and pions and subatomic particles, working with their energies, which they turn into mass, and their charge and with their spin. That's essentially what they do. That's the job of a mathematical physicist, both theoretician as well as the lab guy. And then in 68, they finally had evidence that quarks really do make up protons and neutrons. Until then, it was just theoretical. Okay, you can see starting in 70, I started putting the dates. This is important for you to keep an eye on now. They started putting the dates. I put the dates when they received the Nobel. The dates on the left show when the guy discovered whatever they discovered. And on the right, you'll see, right at the end in parentheses, you'll see the date when they received the Nobel Prize for their discovery. And you can see the quark inelastic scattering, virtual photons can knock out a quark out of a hadron. Okay, that was discovered in 1970. They didn't receive the prize until 1990 for that discovery. 73 predicted bottom and top quarks. They didn't receive the Nobel until 2008, quite a few years later. Asymptotic freedom, very important topic, because again, it's they exchange the gluons, and this is what keeps the quarks bound to each other. In other words, what these people say is that a quark attracts another quark because they exchange gluons. Well, what do you mean by that? How can you exchange little particles of force, whatever that means, and produce attraction? How do you pull? How do you pull by throwing particles? A quark throws a particle at another quark, a down quark at an up quark, for example. Okay, so you threw a gluon at it. How do you produce pull with that, with pitching a ball to the batter? Does he come to the mound? I mean, what is this? What are they talking about? What's the mechanism? Okay, and so asymptotic freedom really is nonsense, because they say that all they're saying is the farther something, if you have a lot of energy, then the effect it has on a quark is less. That the quark is stronger. Like the attraction force only when it's inside the nucleus, and there you have little energy. But if you try to smash it and get lots of energy, well, the quark loses its strength. That's all that asymptotic freedom means. And so these are the terms that they've invented. And so, it loses most of the crowd out there. People look at these terms, they don't even know what they mean anymore and what they're referring to. Okay, so again, it's become an esoteric type of discipline, quantum mechanics. It's for a group of people who understand that language, and they only run into trouble when they have to explain it to the layman, because layman will not want to hear all these terms. They just say, give me the bottom line. Tell me what's happening with little balls or with whatever. Just show me a movie of it. And that's when they have to turn their quantities into little balls. Okay? So again, quantum mechanics is not a ball theory. It's a mathematical description. Okay, the charm quark, fourth type of quark. They had to invent another one. They had 3 quarks inside the atom. They had to invent the fourth one in there. Okay, in 1974. Electroweak interaction, mathematically fine-tuned by a group of people who received their... they did that in 74. They received their prize in 99. They discovered the tau neutrino in 95, the cosmic neutrino. They realized it was created by the sun. Okay, so these were cosmic neutrinos. And again, they discovered that in 80 and received it in 2002. Then they finally detected the W and Z bosons. Okay, 1984, they received the prize 1 year later. That was quick. And then the last, keep in mind, this is the last one, the last discovery. Okay, neutrinos have mass in 2015. They discovered it in 1998. They received the prize in 2015. For the last 20 years, they have not discovered anything inside the atom. Okay, now they discovered the Higgs, but the Higgs is a particle related to mass. It's not. It's like more related to gravity, which is like an outside force. Yeah, they claim it's inside the atom, and they can't find it. And it's like they've given up hope on that. Okay, gravitons, as far as I know, nobody's really researching that in any depth. They're working on something else, which I'll go over in a minute. But the peering into the atom stopped in the year 2000, 1998, whatever, turn of the century. So for 20 years, they have not been looking inside really the atom. The Nobel Prizes they're giving now are for anything in the last couple decades of the 20th century. Okay, 21st century, nothing new inside the atom. Essentially, we bring Niels Bohr back. It's a complete theory. Quantum mechanics is complete, you could say, right? And that's it. That's it for quantum mechanics. So what are the new generations going to be working on? You got the Z generation now, the last generation, as I call it. And what are these people going to be working on? They're going to go to the accelerators. And what's there to do over there? What are they going to be doing? Smashing atoms so that they can see inside the atom? And you say, well, we've got so much energy to produce these collisions. Now you need to have higher energies to break whatever's in there even further. And so they build these bigger colliders now. They're working on all these colliders, making them bigger so that they can be accelerated. The particles can be accelerated with more energy, so they can be smashed with more energy to see if they get the little pieces out of there. Okay, and they're just going to be naming those. They're just going to give new names to these new particles. What's all that for? What is all this work about? This transgenerational, 70-year work all about? Is it just smashing particles, giving names? I mean, assuming that's what they're doing, assuming there are particles, right? Because we have a totally different model for the atom. But assuming there are particles. Okay, so you smashed it. You came up with a quark here, a neutrino over there, and then you got the gluon over here. Okay, fine, you got all these particles. And well, what is this for? What is the purpose of all this? It's just giving them Greek letter names? So all these people just have jobs doing equations. That's all they do. And now they ran out of equations because it's like, we're finished. What more are you going to find in the atom? So they created a new branch of science, not of science, but of quantum mechanics. And it's a branch that sticks its arm all the way from general relativity. And that's this one. It's the dark matter that forms the outside of galaxies. And here you can see the summary, essentially. All these quantum particles, or quantum in general, that deals with the matter that we're familiar with. Atoms, molecules, everything we see every day. That's only 4% of the matter in the universe. And they have all these descriptions. They don't understand any of it, again, because they're not using First, they're not using objects. They're using concepts. They're using amounts. That's the first issue. The second issue is that even if these were particles, the explanation is irrational, because you cannot explain how, first of all, why the electron doesn't fly spontaneously out of the atom, or why it doesn't fall into the nucleus. You cannot explain that, okay? And physically. You can explain it with math, yeah, you put a negative sign, you get it done. But you cannot explain it physically. You cannot show that on the board. You cannot go to the lab and simulate it with balls, with particles, or whatever. You cannot simulate it mentally, let alone in the lab. So we don't have an explanation, even if there were particles, okay? But that's only 4% of the universe. Matter is only 4% according to them, okay? And they say 21% is dark matter. What is dark matter? Well, you have this galaxy rotation problem that you see there, okay? And the galaxy rotation problem is that, a galaxy rotates. First of all, the stars don't fly out. If this is a carousel, why does that star on the outside stay faithful to the center of the galaxy? Why doesn't it fly out? And then the other issue is that they discovered by studying stars going around galaxies that these stars travel as fast or faster than the ones on the inside track. And that's like if Pluto were going faster than Mercury around the sun. How can you explain that? We think that Mercury, because it's on the inside track, goes much faster than Pluto. That's not the case with the stars. The stars, it's the other way around. It's the stars on the outside that go faster. So you say, how can that possibly be? And so they said, we can fix this. And they sprinkled mass, kilograms, out there on the outside, and that's called dark matter. That's what dark matter is about. Okay, so they have that, and so with that they explained in their minds, right, with this ad hoc stuff, they sprinkled matter there, mass, not matter, they sprinkled mass, but they call it dark, not dark mass, they call it dark matter, okay, to show you that they're doing physics, they're still doing physics. Okay, so they have this dark matter out there, and now they can simulate why the galaxy rotates the way it does, okay, and why the stars don't fly out. Fine. But what is this dark matter? Is this just a computer-generated simulation? Is this just an equation? And so they said, hey, you guys at CERN, at SLAC, at LHC, and SLAC and Fermi Lab, why don't you guys look for this dark matter particle, the particles that make up dark matter? Okay, what are we looking for? Well, it's ultra heavy and invisible. Invisible, intangible, apparently, but it's ultra heavy. And so look for it. Okay, so now these colliders are trying to find this dark matter to help the people in general relativity out. It gives both fields of mathematical physics something to do. These guys are doing the calculations, the equations for dark matter, which is already done and it's finished. And these other fellows are going out there and saying, okay, look for it. And so they're saying, okay, let's prepare the collider to see if we can smash particles at such energies, at such force, right? That what comes out of there is a bit of dark matter, and we see it as a trace in some emulsion that they've got in there. We'll see a trace through the hydrogen gas, and that trace has to have these characteristics. If it meets those characteristics, we have found dark matter. Give me my Nobel. That's the way it works. That's what they're into. Okay. And then we have the rest of the ignorance, because we don't know what dark matter is, so they're looking for that. They don't know really what the 4% is, so I'm being kind. There's 100% ignorance, but we'll live with 96. That's close enough. You can round it off if you want. Then you have 75% dark energy. And you say, what the hell is dark energy? And dark energy is, you have this Big Bang that they claim happened, the origin of matter, 14 billion years or so ago. So there was this explosion, which is not an explosion according to some. They don't like to use the word explosion. Okay, so there's this explosion, as I like to say, ground zero, and all the matter was created in this process, and eventually, and it evolved, and it turned into eventually stars and galaxies and etc. Okay, and in the 1929, I think it is 1930, they finally came to the notion that galaxies are flying apart. But it's not just that they're flying apart. They eventually figured out or discovered or measured that they're flying apart at an ever faster rate. Why? Because the galaxies and stars which are farther away from us are flying away faster away from us than the stars that are closer to us. So if you look at the movie in your mind, okay, the stars and galaxies closer to us are going at 60 miles per hour, okay? And the others are going at 120 miles per hour, and the others are going at 500 miles per hour. So the farther out you go, the faster they go. So the universe is exploding in front of our very eyes. That's the notion they have. And you say, well, what's the problem with that? Well, the problem with that is that you've got gravity. They don't know what gravity is. Maybe it's gravitons, maybe it's warp space. Who knows what gravity is, right? And so gravity is supposed to pull all these stars, all this matter, all this 4% matter back together. You know, we should have this oscillating universe, which was one of the proposals originally, right? That the universe explodes and comes back and explodes and comes back. So that was the notion of the oscillating universe. Well, they debunked that. They said, no, it's not going to happen. This thing is going to go out and just fizzle into nothingness. The universe is just going to explode and turn, you know, eventually just wither away. And so you say, what's the issue? The issue is that gravity should be pulling all this stuff back together. What's pushing everything else outwards? That's your dark energy. That's why they had to create dark energy. They created this monster, this invisible ghost that pushes somehow, because energy, you know, is material, it pushes things, right? So energy is pushing all these galaxies outwards, and it's overriding the gravitational attraction. Okay, so that's why they had to create dark energy. Of course, then you have some exceptions which they turn a blind eye to, like our biggest neighbor here, the Andromeda galaxy, which is coming towards us. You say, well, how come that one's blue shifted and coming towards us? That's a fluke. They say, well, you know, somehow gravity is overcoming in that case, right? In other cases that some of the local group, they're coming towards us. Well, in that case, gravity is overriding the electromagnetic or this dark energy repulsion. And that's where we are today. So where are the next Nobels going to come from? Well, they're going to come from dark matter, for one. Maybe string theory, because string theory still is dealing with the graviton and with black holes. So, you know, it's possible that there's going to be a Nobel for the string theorists. On the one hand, one of the problems, the strategic problem the string theorists have is that the Nobels are controlled by the quantum guys. See, when you get a Nobel, you get to vote for the next Nobel guy. And so these guys control the Nobel medals. And they say, okay, who do we give it to next? Well, let's give it to one of our guys, one of our quantum guys. And right now they're giving it to their peers. And these guys, the string theorists, they're on the other side of campus. They don't talk to each other. And they say, well, one day you got to give it to us. See, we've done all this math showing that, you know, what happens to a graviton when it falls into a black hole. You know, and black holes are proven. Gravitons are not proven, but, you know, we know what a graviton is. It's a vibration of a little line, right? And so, you know, you got to give us a Nobel too. And so, and because the new generations, the Z generation, the last generation, has nothing else to work on in quantum mechanics, a lot of them are moving into string theory. They say, well, if I'm going to do math, I'm going to do string math. There's no more math left in quantum. And so a lot of people are choosing that they're going into so-called mathematical physics. They're going into string theory. And so eventually you're going to have such a big group out there that you're not going to be able to deny them a medal. You're going to have to recognize them and say, okay, let's give them a medal. And once they start getting medals, they start voting for their own people, and you'll get more and more string theory medals. Until the quantum guys are able to make an atom smasher big enough to produce dark matter.